In this video, we will be finding the equation of a tangent line by using the derivative function to do so. And so a quick review, remember from algebra class that the equation of a straight line is always given by the point-slope form equation. If you have a point and you have the slope, you can always use this structure as a basic outline. And basically, all we need to know is one point on the curve. That's something that should always be told to you. Like if a question in your homework is going to say, what is the equation of the tangent line? You need to know where, because the line's going to be different depending on the point of tangency, depending on where we want to find it. And then the slope is the other thing. And remember that the slope is determined by the derivative. So basically, first thing we want to do is figure out the derivative of the function, then find the slope and plug in all the information at the specific location. Or you could also follow the step-by-step guide, which I recommend doing, and I'm going to go ahead and do it this way consistently. But basically, it's using a functional form. So it's saying exactly what I just said. Step 1, find the slope of the tangent line, and remember that if I'm trying to find it at a particular point, x is equal to a, that's always going to be equal to the derivative of the function at point a. So first step, find f prime of a, which is equal to this m right here. Then plug a, f of a, and f prime of a into the equation. Y is equal to f prime of a, x minus a plus f of a. And actually, this equation probably looks a little different, but actually this is the same exact equation from before. If we were to just add y1 to the other side of that equation, we would get a consistent formula, which is y is equal to, and usually when we're trying to write the equation of a line, we want it in the form y equal mx plus b. That's, usually most instructions will ask you to write it in slope-intercept form instead of point-slope form. And really that's the gist of how you do that. Just add y1 to the other side and then expand everything else out. But basically notice that everything here is exactly the same. It's y is equal to m. Remember, m is always equal to the derivative at that point. X minus a, where a is just taking the location of x1, so really this is just x1, and y1 is always equal to f of a, because that's how functions work. Input is x, output is y. So if I'm calling this x1, y1 will be equal to f at a, and that's why this makes sense. But let's go ahead and just do the example. So to start off with, if I want to figure out the equation of the tangent line for this function x squared at x equal 2 and x equal 5, first step is I need to know the derivative. And this one we actually did in class this week. So if you recall, the derivative of x squared was equal to 2x. And again, you could verify this yourself by difference quotient if you want. Now that I know that, I can always write the equation of the tangent line by starting off with the formula y is equal to f prime of a times x minus a plus f of a, which again, this is just point-slope form coded for derivatives. And basically, all I need to know is, well, what's a, what's f of a, and what's f prime of a, and that depends on where I'm asking. So we could start off by saying, well, what about at x is equal to 2? This would just be a in this example. So what I want to do is I want to figure out what is f prime of 2. Sorry, my tablet wasn't happy there for a second. Times x minus 2 plus f of 2. Basically, just plug into there. And now I just need to solve all of this stuff. So f prime of 2 would just mean plug 2 into the derivative function, which is 2x. So 2 times 2 is just 4. So basically I'm going to have y is equal to 4. And then that will be multiplied by x minus 2. Remember, I don't plug into x here because I'm trying to find the equation y equal blah, blah, blah x. I want it as an equation. So I'm just plugging in a, and everything else will create the shell for the equation. And then this would be plus f of 2. Now I haven't done f of 2 yet, but that's also coincidentally 4, because remember, f means I'm just plugging it into the original function. Sorry if I'm slurring a little bit. I'm very tired right now, and I'm trying my best to be coherent and clear. But if I plug in 2, this would give me 2 squared, or also 4. And so what I would have is 4. And this would give me the equation for x minus 8 plus 4. And simplifying this, this would leave me with the equation y is equal to 4 x minus 4. And so this would be the equation of the tangent line at x is equal to 2. So first thing is, how do we know that our answer is correct? So one easy way to check is if you look at the graph of your function, you can actually graph your tangent line with it to see, does this look like the proper tangent line at the point of tangency? So to do that, all you need to do is graph both the original f of x and your tangent line on the same graph. So in the TI-84, we can always just type in, well, the original function y is equal to x squared. That's that. And the tangent line is the equation y is equal to 4x minus 4. So you can just type one of them into y1 and the other one into y2. Now if I hit graph, my graph window is a little bit weird because I was doing some stuff in a previous video, but if your viewing window doesn't look very good or doesn't look very normal, one way you can always fix it is by using zoom standard. So if you click zoom and go down to number 6, zoom standard, that will reorient your graph in the normal domain and range of -10 to 10, kind of the normal viewing window that we're used to for a graph. And what we can see here is we have our parabola, which is x, the equation y equal x squared, and then we also have the tangent line. And at that point, if we trace to where x is equal to 2 and hit enter, we can see that we have our point, and it appears as though that tangent line looks good at the point of tangency. And it's kind of hard to tell because this window is not super clear, but you can always zoom in on that particular point, hit enter, and get closer to it to see, okay, does this actually look like a tangent line at that point? And sometimes it might not be very easy to see that, but based on this confirmation, it looks right. And how you can, really, if you're not really sure what to look for, if the line doesn't look, if it's not connected to the curve, touching it at that point, and it doesn't properly model the slope, then it's not right. But in this case, we'll go back to zoom standard. It seems to be touching at the point x is equal to 2, and it seems to have the same slope as well. So obviously doing it mathematically is the better way. It's very algebraic, but or as we say, do the calculus. Solving the calculus helps me figure out the actual slope, so that I can properly write the equation. Now, if I was to do the same thing, let's say I wanted to know what's the slope at x equal to 5 over here. I can't actually see that on this graph, but we'd expect it to be steeper because as you go further and further up the parabola, it's going to get steeper and steeper and steeper. And of course, I could just go ahead and do the math and see. It's going to be a different equation is the thing. So all I would do is I'd need to find, well, what is f prime of 5? And then it would be times x minus 5 plus f of 5. So f prime of 5 would be the derivative at 5. So that would be 2 times 5 is 10. And then plus f of 5 would be plugging 5 into the original. The original is x squared. 5 squared is 25. So what I'm going to have is 10x. I'll go ahead and just rewrite it like this. The equation will be y is equal to 10x. And of course, this would be negative 50 plus 25, which is negative 25. And so this will have a different intercept and a different slope, but that is typical. The equation of the tangent line depends on your point of tangency. We'll always have a different point, and usually we'll have a different slope.